All right, so here we have another example. Hopefully you had a chance to give it a try. Now, whenever you're given a series where you're asked to determine whether it converges or diverges, you kind of have to take some steps. Now, in this particular case, since we're learning the integral test, it's probably a case of applying the integral test. But in general, when you're given these problems and you don't know whether they converge or diverge and you don't know what test to apply, you have to kind of go through a process. And the first thing you should always check is just the test for divergence. Does the nth term go to 0, right? So in this case, the nth term goes to 0, right? So we don't know if it converges or diverges. If it doesn't go to 0, we know it diverges. But if it does go to 0, we really don't know either way whether it converges or diverges, because that test for divergence only tests for divergence for certain cases where the nth term does not go to 0 as n goes to infinity. So if we're going to apply the integral test to this, we always have to make sure that this function 1 over 2 to the n plus 3 is continuous, right? Continuous. It's positive, and it's decreasing on the interval 1 to infinity, right? If that's not true, then we cannot apply the integral test. So it's always good to check that first. But in this case, it is. So what we can do to apply the integral test is I'm just going to integrate it from 1 to t. Now, I want to do the integral from 1 to infinity, right? That's the integral test, is to integrate it to infinity. So I'm going to integrate it to some arbitrary t and then take the limit as t goes to infinity. All right, so the function is 2x plus 3 dx. So I'm changing it to an x because x normally represents real values. So, all right, so what do I get? Now I have to do a substitution in this one. So I'm going to say, I'm just going to kind of do a little side calculation. If I let u be 2x plus 3, then du is equal to 2 dx. So that means that dx, so I can divide both sides by a half, or by 2, sorry. And so I get 1/2 du is equal to dx. So then I can substitute in there. Now I'm just going to do the indefinite integral first, and then worry about integrating from 1 to t. So if I just do the indefinite integral, then I have 1 over u times 1/2 du. Okay, just by doing the substitution. And then what I find out is that gives me 1/2 natural log of u plus c. Okay, so that's my indefinite integral. So that helps me integrate from 1 to t, because that means that if I take that indefinite integral, so 1/2 natural log, now u is 2x plus 3, so 2x plus 3, and I evaluate that from 1 to t, right? Then I'll get the integral from 1 to t. So what do I get when I do that? I'm going to pull the 1/2 out front, and I get the natural log of 2t plus 3, absolute value. And then when I substitute 1 in, I'm going to have the natural log of, looks like 2 plus 3 is 5. So I get the natural log of 5. I don't need the absolute values because obviously 5 is already positive. All right, so that's the integral from 1 to t, and then to get the integral from 1 to infinity, so the integral from 1 to infinity of 1 over 2x plus 3 dx is equal to the limit as t goes to infinity. And so I get, let's see, this was, I'm just going to actually distribute the net, or the 1/2. Natural log of 2t plus 3 minus 1/2 natural log of 5. Okay, and you can see that this natural log part goes to infinity. So that means the whole thing goes to infinity. So the limit is infinity. And so this is another one where the series diverges. So we can just state our conclusion. Therefore, the series diverges by the integral test. Integral test. Okay, so it diverges. I'm going to emphasize that. All right, so the next example is a very important P series. So I will meet you for the next video.